Okay, questions. Last time we had rates. Average rate of change, instantaneous rate of change, 2.3. Number 11. Okay, what's going on with 11? Consumer trends. The graph shows a number of visitors to a national park in hundreds of thousands during a one-year period. And evidently, so each T equals a month. Okay, T equals 1 represents January. A, estimate the rate of change of V over the interval 9, 12. Okay, well, without resketching the graph, I'll just give you a rough idea how. Do you have a question about A? Okay, so you've got a graph that goes something like this. And let's just say for the time being that 9 is somewhere in here. And what was the other one?
12.
12, and 12 is near, right by the bottom somewhere. Now, this isn't done very well because that's supposed to be curved. But what you would do is take a point as close as you can to where 9 hits, pick a point as close as you can to where 12 hits. Literally, think of it as being a line or segment that connects the two. And then basically what you want to do is find the slope. So, you could just get the two ordered pairs, which are what? Estimate, what's 9? Well, what did you estimate that as? 1350?
Yeah, 1400.
What'd you say?
1400.
1400 is fine. So 9. And then 12. What is that, 0? Okay, find the slope. Doesn't really matter. I'll say 0.1, 0.2, y2 minus y1 over x2 minus x1 negative 1400 over 3. And then if you can simplify it, you can. That would be what I would call the average rate of change. And what is that? Negative 400 something?
466.
Thank you. Now what does that mean? That means for every month, this thing, the number of visitors decreases 466, what is it? 100,000? Since each thing stands for 100,000. Wow. So why is that? Of course, there's an obvious reason for that. As we head toward the winter months, a lot of the national parks are in a place where winter will hit, and so less people, yeah, that makes sense. Okay, now part B. Over what interval is the average rate of change approximately equal to the rate of change at t equals 8? Well, t equals 8, just by eyeballing, appears to be kind of at the top point of the graph, doesn't it? And so wouldn't you agree that it looks like the slope of the tangent line there appears to be about 0? And so the question is, over what interval is the average rate of change about the same as that, 0? And there isn't, about the only thing you could say, the closest would be what? During January to February, when the slope is pretty slim. But really, is there any time where it's going to average? Well, oh, I see. Well, here's another thing you could do. I just realized what they're getting at. You could take their overall graph and say, okay, up on top here, here's the slope of your tangent line at 8, correct? In this red line. What other period could give you an average of that? And all you got to do is pick 2 points that when you line them up, you would get a horizontal line, because you're talking average rate of change. So you could pick any 2 points that you know, connect to be about an average, about 0. So I could pick, let's say, 6 comma 10 almost. That's a little bit off, but you see how if we took 6 and 10 and connected them, what would we get for an average rate of change? Fairly close to horizontal. So I could say, what is that? 6 is June through October. Or you could pick any other 2 points that might do it better than that at least come out to be horizontal. That's the idea of part B. Okay? Yes. 37, yes. See if I got that first. Ah, how about that? There's 37, the next one. Okay, reading. Marginal profit. When a glass of lemonade at a lemonade stand was 75 cents, there were 400 glasses sold. When the price went down to 50 cents, 500 glasses were sold. Assume that the demand function is linear and that the variable and fixed costs are 5 cents and 20 bucks respectively. Okay, so I put my two ordered pairs down. 75 cents, we sold 400. 50 cents, we sold 500. Makes sense. We're going to sell more when the price goes down. Probably. So from that, I calculated a slope. I did 500 minus 400. That's where I got the 100 on the top. And 50 cents minus 75 cents is a negative 25 cents. And that gives you a negative 400 for a slope. So now I started writing the equation of a line because they said the demand function, didn't they say linear? Yeah, they said assuming that the demand function is linear. Okay, so y equals negative 400x plus b. Now, I plugged in a point. I took the 75 cents 400 point, plugged it in, and I was able to calculate b. So that gave me a y-intercept of 700. So now here's my, let me just stop and see if everybody sees how I got here. Here's my linear demand function. And I got it by just taking these 2 points, calculating the slope, calculating the y-intercept. Okay, now I renamed it as small p because that's what the business people like to call the demand function. Okay. We're together there. The next part says, find the profit p as a function of x. Well, all right, how do you find profit? It's revenue minus costs. So now, where did I get the revenue equation? You take x times the demand function. So I simply took negative 400x plus 700, multiplied it by x. That gave me negative 400x squared plus 700x. Now, the cost. Well, they said fixed costs a nickel. That means every time you make a glass of lemonade, it costs you 5 cents in materials. Okay? And then, I'm sorry, that's the variable. And the fixed cost is 20 bucks. I suppose for a pitcher and some glasses and a table and maybe a custom for sale, lemonade for sale sign, whatever, costs 20 bucks. So the cost function is 5 cents times x, a nickel for every glass plus 20 bucks. So now, finally, subtract the cost from the revenue and you've got the profit. So I took, it's messy, but what I did here is I did revenue minus cost. So this equation minus this equation, and it should be what I have here. Negative 400x squared, and then plus 700x, subtract this guy, 5 cents x minus 20. Here's what it came out to. So that's part A. What's B? Using the graphing utility to graph P and the comment about the slopes of P, what What comment? Does anybody know what they're talking about when they say that comment there? What am I missing? I'm on 37B. I'm probably missing something incredibly obvious. And oh, you're supposed to make a comment. Ah, how so? Okay. My apologies. Slow day. Let's quick plot it. Okay. So I'll get this up high enough so I can see my function. So we got to do negative 400 times x squared plus, what is that? 699.05x. And then minus 20. Okay, obviously we got to zoom out. Let's try in. And hang on a second, I can't remember, how do I... Oh, there we go. What in the world's going on here? Let me double check if I need to nope. We should have a parabola, and I'm not seeing one here. Whoa, finally getting the top of a parabola. A very skinny parabola. Okay, so now what's the question? After looking at the graph, comment about the slopes of P when x is 200 and when x is 400. Okay. Got to get back to my x-axis. Well, they're going to be very steep, aren't they? What did I do wrong? This doesn't seem like a logical question. Let me just, I mean, right now I would just say, I mean, here we got this parabola that only goes from 0 to 1 on the x-axis. So what's going to happen at x equals 200? We're going to be way out there, and it's going to be very steeply downhill. And so I'm wondering if I did something incorrect here. Anybody double check, is my, how's my demand function according to them? Did anybody take a look at that negative 400x plus the part A answer? That looks correct? The what? So this profit is not what they have? Okay, well, okay, let me just double check. If we take a demand function and multiply it by x, that is correct. Now if I take r and subtract c, I should get this. What did I... So they don't agree with profit at all, huh? I got to take a look at this because I'm so far in another county that I got to see what's going on. Okay, where are we? This is 2.3. 33, number 37, B. No. Yeah. 2.7 always takes me forever just to find this. 2.4. What is this, 2.3? Thank you. Okay. Well, they got a parabola, but it sure doesn't look like mine. What did I do? Oh, they've got, oh my. They have the slope of the value is negative 0.0025x squared. And I've got 400. What did they do? I don't know. I'm going to have to think about that one. So let's look at A. No, they don't have what I have for A either. Okay, so we disagree way back there. What did I do wrong? Back to A. $0.75 for, oh, you know what I'll bet they did? I'll bet they reversed the variables. I'll bet they had 400 comma 75 cents and 500 comma 50 cents. That's not what I see in the book. You saw that in there? Oh, okay. I don't know. It looks like I've done this right. I'm going to have to take another look at it maybe outside of class. Yeah. Oh, they solve for x. Why did they solve for x?
So they're using instead of x and y, they're using p and x.
Yeah, well, I did too here. P and x. Cover that one up. Yeah. But then they solve for x. Why did they solve for x? You want a function of x when you have a demand function, and then you want to multiply. I'm gonna have to get back to you guys on this. It looks like I still don't see an error, but obviously there's something goofed up. Sorry, but I don't want to take too much time on one question. So I promise you I'll get back to you on this one. 37. Okay. Well, do we have another one? Would anybody be brave enough? John? 33? Okay, temperature of a person during an illness is negative 0.0375. T squared plus 0.3t plus 100.4. Okay, what do those letters stand for? T, capital T is temperature and T is time in hours, since a person started to show signs of fever. Use a graphing utility to graph it. Did you want me to do that? I guess I may.
Yeah.
Okay. Will do. So let's just not show that other one. Okay, should look something like that. Now, part B, where are we? 33B. Do the slopes of the tangent lines appear to be positive or negative? That depends on where, doesn't it? Obviously, we're not going to do negative time because that would be before you got a fever. So the left portion of this graph obviously is not going to do much, right? So it looks to me like if I zoom in a little bit here, you're going to have, I would just make this comment. There are going to be some negative slopes from up until about in here, which is going to be how many? I would say for the first 5 hours, there are positive slopes, and after that, they appear to be negative. So what does that mean? It means in the beginning, the fever is still increasing, but then after, I think those were hours, weren't they? Yeah. After 5 hours, it appears that the fever will break, so to speak, and start decreasing. So that would be my interpretation. Part C, evaluate the function for t equals 0, 4, 8, and 12. Now you just take the function and plug those numbers in. You probably don't need me to show you that. Part D, find dt dt. Find the derivative of the thing and explain its meaning in this situation. Okay, well, I don't know, you can do the derivative, a simple power rule. What does it mean? That's the formula for the rate of change of his temperature at any instant. And we should again see that up until 5 it's increasing, and after that it's obviously going to be a negative. And we could even find when is it 0? That is, when does the fever break? How would we do that? Find the derivative, set the derivative equal to 0. And that wouldn't be too hard, because what's the derivative of a second degree equation? A first, right? The power always goes down. And so all we would have for a derivative is a linear equation. Pretty easy to solve for 0. You don't have to do quadratic or factoring or anything like that. You want me to show that? Okay. So there's 33. Let's see, there was another hand. Yes. 39. The marginal profit refers back to 38. Suppose ticket sales decreased to 30,000 when the pricing. Okay, so let's go back and see what 33. We got to look at 38 in order to do this. Back on 38, it says when they sold the tickets for $6 a ticket, they sold 36,000. When they raised it to 7, 33,000. And now, what does it say in number 39? Oh, they changed it. When the price increased to 7, it went to 30,000. Okay. I see, they changed the number in that one. Okay, so there's our ordered pairs. Now, how would this change the answers? Okay, well, so we got to go back and think through number 38 using the new answers. Well, what's the profit as a function? Okay. Well, first of all, wow, we got to go back and we got to find the demand here. So, once again, I got to find the slope. This is, I'm calling this 0.2 and this one 0.1 because 0.2 occurs later when x is bigger. And then x2 minus x1. So we got negative 6,000 over 1 So negative 6,000. So now I know the beginning of my linear equation for demand. Now, I got to tell you what X is. X is what? The cost per ticket. You know, I'm just getting, things are maybe clearing up on her problem. I was using X for cost. And when you get to profit, X doesn't stand for cost, it stands for units. Now I see why they changed back on that one. Okay, this is becoming clear. Okay. Actually, yeah, here's the problem. In this problem, X right now stands for what? What was this first number? The cost per ticket? And so I can go ahead and finish this, but when I get all done, what does Y stand for? How many tickets you sold? That needs to be X, and that's why we had to go back and resolve. Okay, it's clearing up. Anyway, let's finish this. Let's find B. Plug in a point. Let's plug in 30,000 for Y, and 7. That's supposed to be 6,000. And 7 for X. 30,000 equals negative 42,000 plus B. So now I know when I add 42,000 to both sides. Okay, so my little equation is negative 6,000 X plus 72,000. But in my equation, X is price per ticket, and this is number of tickets. Well, whenever you do a profit equation or a cost equation, what does X stand for? The number of units, the number of tickets. So here's why we got to solve for the X. Okay, so let's quick do that. We would first subtract 72,000 from both sides. Equals negative 6,000 X. And then solve for X, divide both sides by negative 6,000. Well, six thousand goes into 72,000 how many times? 12 times, right? Okay, so now we have ourselves a demand equation. And we could use the different variables now. Let's write it this way. I'm just writing the negative x over 6,000 as negative 1/6,000 times x. Okay, now there's demand. Now move on. Okay, what's revenue? Revenue equals demand times x. So revenue is equal to negative 1/6,000 x squared plus 12x. Okay, getting there. Sorry, this is sloppy. Now we got to do what? We got to get the profit, so what's the cost? What did the problem say? Fixed costs are 20 Variable costs are 20 cents a ticket, and 85,000. So cost is 0.20x plus 85,000. Is that right? 85,000? And that must be what? Some kind of an amortized, how much the ballpark cost type thing or something. All the huge costs that would come into having a Major League Baseball game. Finally, what's profit? Revenue minus cost. So this thing minus this thing. So we have negative 1/6000th x squared plus this minus this. Well, that's negative 0.08x, right? If you take 0.12x, no, that's not correct. Let me get that fixed. What's 12 minus 0.20? It's 11.80. And then we have to subtract 85 thou. Okay, last step, I think. You wanted marginal profit? So what do you do? If that's profit, how do you find marginal profit? Well, this is P of x. You need P prime of x. So now differentiate. What is, it's negative 2 over 6,000, which is what? Negative 1 over 3,000? Reduce the power of x plus 11.8. This drops off. Okay, for doing it all pretty quickly, that's what I come up with for a marginal profit equation in 39 where we altered number 38. Yeah, and that is the problem now that I can see back on your question. Yeah, now I can see why they had to resolve that. Okay, well, we got to get some new stuff done here. So, let me try to find my way. Here we go. Now, I've only really taught you one rule, haven't I, for shortcuts for derivatives? And it's been called the power rule. Well, I'm teaching two additions to that today. The product rule and the quotient rule. Why do I have to teach these to you? Because they're not covered in the power rule. And the power rule is pretty simple. You got a coefficient, you got a variable, and you got a power. But what happens when you have two things being multiplied or two things being divided? And that's where these two rules come in. So here's the product rule. Now, it's not as bad as it looks. Here, let me cover it up so you're out of pain for a little bit longer. Okay. Here's the product rule. You got part A times part B. I'm not showing it to you anymore, so if you couldn't get it down in that time, that's just too bad.
I got it.
Not true. Yeah, you got a mental image here already. Cool. Let's say we got function f multiplied by function g. How do you find the derivative of those two when they're being multiplied? The answer is you take the first times the derivative of the second plus the second times the derivative of the first. It's really not that hard when you hear it that way. So you got f and g. What's the derivative of f of x times g of x? It's f of x times g prime of x plus g of x times f prime of x. Well, that's basically it. And now we'll start to uncover. So you see, there's the product rule. That's what I was just saying in words. I've got the words up there too for you. I copied this particular section. I copied from the guy who wrote the online calculus site. That's me. So I figured I should give credit. I don't know why I said that. But anyway, that's how you do the product rule. Now, this big obnoxious thing that was underneath it that Han had memorized already was an example. So Here's an example. Here's an example of two things clearly being multiplied, right? In function h of x, I've got a trinomial being multiplied by a binomial. 3x squared minus 14x plus 1 multiplied by x squared minus 9. Now, honestly, don't multiply it out right now, okay? Just take my word for it, because it's the whole point of this is I want to show you how it works. So let's just say my answer there is right. 3x to the fourth minus 14x cubed minus 26x squared plus 126x minus 9. Now, it's easy to find the derivative, isn't it? You just use the power rule. And so 4 times 3 is 12, and you get 12x cubed. And 2 times negative 26 is negative 52. That should be 52. And then reduce the power by 1. 1 times 1. Oh, I was doing the other term. I'm getting mixed up between my terms, so it was okay. That was 3 times 14, which is 42. Okay, now I see. And then 2 times 26, there's the 52. Okay. So anyway, there's nothing new here. This is called how do you multiply, and then how do you take a derivative. You already knew how to do those two things. Okay? But combine them, and you can do the product rule. And I'd like to demonstrate that the product rule really works. So now let's follow the product rule. Let's take the first times the derivative of the second. What's the derivative of the second? 2x, right? So take the first guy, multiply by the derivative of the second. That's this part right here. Plus, take the second guy, x squared minus 9, and multiply him by the derivative of the first guy. What's the derivative of this guy? 6x minus 14. Okay, so we work it out, and sure enough, look it, you get the same answer. Now you're probably thinking, why would I do that when I can just multiply them and take the derivative? And the answer is sometimes you just can't do the multiplication very easily, and the rule becomes important. Yes? What is this? Okay. Yeah. Listen. This is the first factor times the derivative of the second factor plus the second factor times the derivative of the first factor. So 6x minus 14 is the derivative of this guy. You're welcome. Okay, product rule. Let's do an example, huh? Another. So, see if I can take one from the book. So on page 128. I don't know, let's just do 23. So this is 2.4, number 23. It says find the derivative, and let's use our new product rule. The function is first quantity x cubed minus 3x. Second quantity 2x squared plus 3x plus 5. Okay, use the product rule. So here we go. Derivative. Take the first factor times the derivative of the second plus the second factor times the derivative of the first. I don't have room, so I'll stick it right down here. Okay, so now it's just a matter of mechanics. So, but that's basically the rule. The first times the derivative of the second plus the second times the derivative of the first. The way I learn things is by words. And so if you're wondering why do I keep repeating that, I think that's the best way to get it up here. You're not going to remember, you're not going to memorize symbols. You got to memorize, for me, words get it up here. But so anyway, let's multiply. What's x cubed times 4x? X cubed times 3. Negative 3x times positive 4x. And negative 3x times 3. Okay, look right. So there's like, I'm just going to do this for convenience. There's kind of the answer to the first product. Okay, what's the second product? 2x squared times 3x squared is 6x to the fourth. 2x squared times negative 3 is negative 6x squared. Three x times 3x squared is 9x cubed. 3x times negative 3 is negative 6x. 3 times 3x squared is that a 3? No, that's a 5. Sorry. 5 times 3x squared is 15x squared. And 5 times negative 3 is negative 15. Okay. And what did I say? 6x squared? Where in the world is that? Right here? Okay, I lost my way. So let me get back here. 2x squared times 3x squared. Okay, that's right. 2x squared times negative 3 is negative 6x squared. That's why I wrote that there. Okay, that's fine. Then 3x times 3x squared is 9x squared. And where did I write that? I didn't. My apologies. Here I thought I'd have a nice organized... I gotta go back. 2x squared times 3x squared is 6x to the fourth. That's correct. 2x squared times minus 3 is minus 6x squared. 3x times 3x is 9x cubed, like I have. 3x times negative 3 is negative 9x. Now do the 5s. 5 times 3x squared is positive 15x squared. And finally, 5 times negative 3 is negative 15. Okay, so there was one line there. Now, if you can follow all of that, we're going to add it all up. That would give us 10x to the fourth, positive 12x cubed. What do we have? Negative 18x squared plus 15 is negative 3x squared. Negative 18x minus 15. Playing games up here? Okay. Product rule. Second rule today. We'll just at least introduce it. Looks like we're running out of time. It's called the quotient rule. And again, I'll tell you what, let me give it to you in words first, and then I'll show it to you. In words, here it is. Now this time you got one function divided by another function, and you want to take the derivative. Okay, the derivative is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the denominator squared. That's as good as I can. I didn't say it was easy. I'm just saying that's as good as I can do it. Here it is again. Denominator times derivative of numerator. Denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. And here it is. Here's what it looks like. It doesn't look as bad when you use symbols. It's just those words, denominator, numerator, are very long. So do you see how it says g of x times f prime of x? That's me saying denominator times derivative of numerator minus f of x times g prime of x all over g of x squared. Yeah, I'm sorry, there is just no shorter way to do this. Yep.
Say the word one more time.
Yes. Denominator times derivative of numerator minus numerator times derivative of denominator. And that whole thing is over denominator squared. Okay, that's the quotient rule, and I'm going to have to demonstrate it for you next time. So, to be continued. Just didn't get far enough today. So your assignment for tomorrow is to come to class.
Are we collecting?
Am I what?
Are we collecting?
I don't know.
You said come class, so I thought we were collecting.
Yeah, I was planning on doing it today, but I changed my mind. Well, I'm just not going to do it today. I take it you spread the word?
Let everybody know we're collecting. I'll talk to you about it.